As you all know what current is, we will introduce a new physical quantity which is called as current density. So current is actually the directed flow of charges. So you can say that current is directed flow of charges. Is a directed flow of charges, or more specifically we can say it is a directed flow of charge carriers, because charge carriers might differ on the material that we are taking. If we are concerned about conductors, then charge carriers are simply free electrons. But if we consider semiconductors, then these charge carriers are negative electrons and positive holes. But for the time being, we shall restrict our discussion to current flowing through metallic conductors, and so for us the directed flow of charges will refer to free electrons only. So charges, or more generally we can say charge carriers. In case of metals, the charge carriers are electrons. Okay. So when we try to measure what current is, we actually measure its strength by the net charge flowing through any cross section of a conductor in a given time interval. So strength of current, you can say strength of current is measured by the net flow of charge, across any cross-sectional area, of cross-section of a conductor in a given time interval. So on the basis of this, we can define current to be either a steady current if Q amount of charge flows through a conductor in time t, then we can say I equal to Q upon T. Or simply we can say the current is the rate of flow of charges, provided the current is a steady current. It always has a constant value. However, if delta Q represents the amount of charge that flows through any cross section of the conductor in a time interval, say delta t, then you can say on an average the current is constant, and that average value of current, average current is delta Q by delta T, whereas delta Q is the amount of charge flowing through a certain cross-sectional area in a time interval, that is suppose delta T. But if the rate of flow of charge is variable, if it is varied with time, then we have to consider what is called as the instantaneous current. And this instantaneous current is equal to the limiting value of this average current, provided the time interval is very small, and that will be expressed as dq by dt, or the differential coefficient of charge with respect to time. So in this manner we can arrive at the definition of steady current and variable current. So instantaneous current is the current that we are referring whenever the current varies with time. If the current is a function of time, or if the flow of charge is a function of time, then we talk about instantaneous current. And average refers to the current that passes through any cross section of a conductor in a given time interval. And if the amount of charge flowing through any cross section is constant for a given time interval, then we talk of steady current. So this is the situation I instantaneous where we are talking about variable current. The current is varying with time. So if you try to represent graphically a steady current and a variable current, the approximate graph might be like this. For a steady current, the magnitude of the current remains constant throughout. This is a graph for steady current, and this will be somewhat, suppose the current grows with time in some manner. So this is a variable current. The current is a function of time. So this is a variable current, whereas this graph represents steady current. So now, if current is expressed as dq by dt, that is the instantaneous current, then you can always find the amount of charge flowing through any cross section of the conductor in a given time interval. So this will become I dt. But current itself is a function of time, and suppose the appropriate time interval is provided. Suppose in the time interval delta t we want to find what is the amount of charge flowing, then we have to integrate this between the limits t1 to t2, provided we know how current varies with time. So now, current, however it is defined, is actually a macroscopic quantity. It is a quantity which has been defined for the entire conductor. Current is a macroscopic quantity in that sense, because it is defined for the entire conductor. Current is a macroscopic quantity. It is essentially a scalar quantity, and it does not obey the laws of vector algebra. So current is a macroscopic quantity as it is defined for the entire conductor. It is defined for the entire conductor. That means for any instant of time, we say that this much amount of current is flowing through the conductor. We don't say this value of current is flowing through this particular section of the conductor. That we cannot say. So for that, we require another physical quantity which is called as current density. So current is a macroscopic quantity. It is essentially a scalar quantity because it does not obey the laws of vector algebra. It has a direction, and the direction is opposite to the flow of electrons. So that's why the direction that we associate with current is just a convention. We assume that current flows in the direction opposite to that of electrons, and it does not obey the laws of vector algebra. Obey the laws of vector algebra. So we say that current is a scalar quantity. Now we can define another physical quantity which is a microscopic quantity. That means it is a characteristic of a certain point of a conductor, unlike the current, which is a characteristic of the entire conductor. So we define what is called as current density. Which is a microscopic quantity. And it is not defined for the entire conductor, it is defined for a particular point of a conductor. Unlike current density, we will see that it is a vector quantity, and so we can also say that current density is a vector point function. It is a microscopic quantity and is a characteristic of a certain point of a conductor, because it varies from point to point. At a certain point it can have a value, at another point it can have a different value. So it is also called as a vector point function. It is essentially a vector quantity and is a vector point function. So now, if the flow of current is uniform throughout the conductor, then this current density will be defined as current per unit area. Current density, if the current is constant, let me call it as J, will be defined as simply current per unit area of the conductor, per unit area of cross section of the conductor. However, it might happen that the current is not uniformly distributed over any cross section of the conductor. If the current is not uniformly distributed over any cross section of the conductor, then we have to define it by some different way. So suppose whenever we define current density, we define it for a particular point, and suppose current is flowing in a specific direction and we have an area of cross section. Suppose this is the direction in which current is flowing, and we have an area of cross section which is not perpendicular to the direction of the flow of current. So this area has to be aligned perpendicular to the direction of current, because current density will be defined as current per unit area perpendicular to the direction of flow of current. So this is current per unit area perpendicular to the direction of flow of current. So if an area is not indeed perpendicular to the direction of flow of current, then we have to align it in the direction of current. So suppose this is the direction of the unit vector normal to this given area. Then in order to align it along the direction of the current, we have to rotate it by that angle theta, which it makes with the direction of current, so that we can get the area perpendicular to the direction of current. And as such, because area is a vector and this current density is also a vector, we say the current is the dot product of current density vector and area vector. Or you can say that I is JA cos theta. Theta is the angle between the current density vector and the area vector. So in that sense, you can say the current density is I by A cos theta, where A cos theta represents the component of the area that is along the direction of the current. That means the area has been made perpendicular to the direction of the current. So whenever we are defining current density as current per unit area perpendicular, we must remember that this current, the area should be held perpendicular to the direction of the flow of current. So we can say that if we define current density is current per unit area, perpendicular to the direction of flow of current. Perpendicular to the direction of flow of current. if the area of cross section is not uniform or the current is not distributed uniformly over any cross section of the area, any cross section of the conductor, then in that case the most general definition of current density will be I equal to integral of j vector dot dA vector. This will be the most general definition of current density when the current is neither uniformly distributed over any cross section of the conductor, neither any area of cross section is in that sense having a regular geometrical shape. So we will define current density in this form. So current density is a vector quantity and it is defined for a particular point within a conductor, and as such it is a microscopic quantity. Unlike current, which is a macroscopic quantity, and a current is a scalar quantity. So now we will look at the free electron theory of conductors and how current is related to the drift velocity and current density is related to the drift velocity. So as we all know that metals are made up of a large number of free electrons, and these free electrons in a metal are always having a random thermal velocity. Free electrons in a metal, they move randomly and haphazardly, and they have a velocity which is called as random thermal velocity. They possess this random thermal velocity because the free electrons behave much like the molecules of a gas, which are randomly vibrating with all possible velocities in all possible directions. As such, the free electrons in a metal are said to have a random thermal velocity. Now this thermal velocity is definitely temperature dependent. More is the temperature of the metallic conductor, the motion of the free electrons will be more random, they will be more haphazard. On an average, this velocity turns out to be 0. For a particular electron, the velocity is not 0, but for all the electrons, all the free electrons in the metal, if we take the average of their velocities, then that average velocity is 0. So we can say that average thermal velocity is 0. Average thermal velocity is 0. So suppose there are n number of free electrons. Let n be the number of free electrons in a metallic conductor. There are millions of free electrons, we know that, in a metallic conductor. Suppose we assume that there are n number of free electrons in a conductor, and let their velocities be u1 vector, u2 vector, and so on up to un vector. So this average thermal velocity, which is just the vector sum of all these velocities divided by the number of free electrons, that happens to be 0. Now, whenever the metallic conductor is connected to a source of potential like a battery or a cell, these free electrons, they get a more organized motion, they get a directed flow. And when there is a directed flow of free electrons, we say that a current flows through the conductor. Unless the metallic conductor is connected to a battery, the electrons are randomly moving in all possible directions. So at any instant of time, if you consider any cross section of the conductor, there are as many electrons entering that cross section as there are electrons leaving the cross section. So we cannot say that current flows through the conductor when it is not connected to a source of potential or a battery. So that's why we say that the average thermal velocity is 0, and that does not account for any current. So suppose we connect, when we connect the conductor to the terminals of a battery, an electric field is set up within the conductor. An electric field, say E vector, is set in the conductor. Now, due to this electric field, there is a separation of charges, and now the free electrons can drift in a specific direction, and as we get a directed flow of electrons, we now say that there is a current flowing across the conductor. So, suppose we take a metallic conductor and we connect it to the terminals of a battery. Definitely, because a battery or a cell is a source of energy, the battery will set up an electric field. Suppose this electric field is E vector, which will be directed from the positive potential to the negative potential, and the electrons will drift opposite to the direction of the flow of electrons. Opposite to the direction of the electric field. Actually, what happens is that the free electrons in the conductor will be all pushed to one side. So suppose this area of cross section now consists of electrons only, and this cross section there is a loss of electrons, you can say. So this will acquire a positive charge, and this cross section will acquire a negative charge. So one end of there will be charge accumulation, or electrons will come towards the end of the conductor against the direction of the electric field, and obviously if electrons have moved to one end, then due to the absence of electrons, a positive charge will develop at this end, suppose, and the negative charge is developed at this end. The battery or the source of EMF is the driver of these electrons, and they will circulate the electrons to the connecting wire, and therefore a current will start flowing in the direction of the electric field, that is the direction opposite to the left of the electrons. So now, whenever the electrons are having a random thermal motion, they are always colliding with the positive metal ions and with other electrons also. So the free electrons collide with the positive metal ions of the conductor. And so the direction of their velocity changes. Now suppose there is a free electron here. At this point, suppose there is a free electron. So it was heading towards the direction, and suppose it has collided with a positive metal ion. It changes its direction, and there suppose it collides with another one. It changes its direction, again suppose it collides with another one, another positive metal ion. So these collisions are always occurring because the random thermal velocity is always present. It frequently changes its path, and many such collisions occur. And suppose we see that the electron has travelled up to this point. So from the point X to the point Y, it has got displaced. but during this displacement it has collided several times with different positive metal ions, and its route has changed. So on an average, you can say that this electron has displaced by the amount x, y. But actually, it has covered quite a large distance because it has frequently collided with other positive metal ions of the conductor. And this occurs because the electrons are always having a random thermal motion. Now, in the presence of this electric field, the motion of the electrons becomes a bit organized. So, whenever they collide with any positive metal ion due to the random thermal velocities, the electric field accelerates the electron, and as it accelerates, its velocity increases. But whenever it again collides with another positive metal ion, its velocity reduces to a greater extent. Then, in between two successive collisions, the electric field is always trying to accelerate the electron. But in spite of these accelerations, the net motion of the electron is not an accelerated one. The net motion is not an accelerated one. The net motion is rather a motion with a constant velocity. So you can say, though this electric field accelerates the electrons, their motion is not a purely accelerated motion, because after each acceleration or each gain in velocity that the electron acquires, they will almost collide with another positive metal ion, and their velocity will get reduced. So it is not a purely accelerated motion. And this motion is called as a drift motion. So in between two collisions, the electron is being accelerated by the electric field, but again the gain in velocity that the electron will acquire, at the next collision it will almost lose whatever velocity it has gained. On an average, we can say that the motion of the electron is a drift motion, and which is a motion with a constant velocity. So on an average, this is what we can say. On an average, the motion of the electrons is a drift motion, and that is a motion with a constant velocity. Constant velocity, and this velocity is called the drift velocity. So we can say that whenever we connect the conductor to the ends or to the terminals of a battery, the electrons drift from the negative terminal of the battery towards the positive terminal. So this velocity is called as drift velocity. So in between two successive collisions, the time that has elapsed is called as relaxation time. Time that has elapsed between two successive collisions with the positive metal ions. Successive collisions is called relaxation time. And during this time, the electric field has exerted a force and has accelerated the electron, due to which it has gained a velocity. But as I have already told, the gain in velocity is practically meaningless in terms of the electron, because immediately it will collide with some other positive metal ions and lose its velocity. Because there is always the presence of the thermal velocity, and the acceleration of the electrons under the effect of the electric field, you can say it is just temporary, because it exists whenever the battery is being connected, but the random thermal velocity is always there. So this time is called as the relaxation time, and the distance between two successive collisions is called as mean path. It is called as the free path. If you take the average of all the free paths, it will be called as mean free path. So the time that has elapsed between two successive collisions is called relaxation time. So suppose this is the initial position of an electron, position x. This is the position of an electron. The electron is moving. It has collided with another positive metal ion. It has changed its direction of motion. It has collided with another positive metal ion. It has moved towards another direction, collided with another positive metal ion, and this happens continuously. So between two successive collisions, the time that it takes is called as the relaxation time, and that is called as denoted as tau. It is called as the relaxation time. It is denoted as tau. The relaxation time is different for different free electrons, but if you minutely observe, it travels quite a large distance. We cannot say that the average speed of the electrons is less. We can say that the average velocity of the electron is less, because after collision, suppose the electron moves along this direction, and suppose now its position is position y. So on an average, you can say this is the displacement. So whenever we are calculating average velocity, it is equal to the displacement by the time taken. But when we are calculating the average speed, we have to consider this entire distance. So average speed is much greater than the average velocity. The average speed of the electron is much greater than the average velocity of the electron. But we are talking about average velocity. And this motion that we realize is called as the drift motion. We can say that the electron has drifted from x to y. But in between, it has collided several times with different positive metal ions, and between each collision, the electric field has tried to accelerate it. So suppose the acceleration that the electron will acquire can be calculated from the magnitude of the electric field. We know that the force on the electron is equal to the charge of the electron into the electric field. If the mass of the electron is m, its acceleration is a, then this is obviously minus e vector by m. So this means the electron get accelerated in the direction opposite to that of the electric field. Now, the initial velocity was the thermal velocity, and due to the application of the electric field, they have gained an acceleration and their velocity has changed. As we have already considered that there are n such free electrons in a conductor, we can say that velocity of one electron is its initial thermal velocity plus this acceleration into the relaxation time. Because relaxation time is the time between two successive collisions, and during this the acceleration has actually occurred. Similarly, for another electron, you can say this is u2 vector plus a tau 2, and so on. For the last electron, the nth electron, we can say it is un plus a vector Tn. So now, if we calculate the average of all these velocities, as we have said that the electrons on an average, they move with a constant velocity. This quantity is called as the drift velocity. That is equal to u1 plus u2 un by n plus a vector tau 1 plus tau 2 by n. This quantity is called as the drift velocity, Vd. This is already 0. We have calculated the average thermal velocity is 0. And this quantity, tau 1 plus tau 2 up to tau n by n, that is the average relaxation time. This tau is the average relaxation time. So now, as we have already calculated this acceleration as minus e by m, so we can write the drift velocity is equal to minus e tau by m. So the drift velocity depends on the electric field, it depends on the relaxation time and the charge to mass ratio of the charged particle, that is the electron. Now you can relate the current flowing through the conductor with this drift velocity. So if we ignore the vector nature of the velocity, etc., if you take the magnitude only, we can write the drift velocity is equal to the charge of the electron, the electric field, the relaxation time by the mass. This is the magnitude of the drift velocity, which is constant. Now we again refer to the same conductor. As we have connected it to the terminals of a battery, which is capable of delivering a constant potential difference V and an electric field E vector. So if the length of the conductor is L, then as we know that electric field is the negative of potential gradient, we can say that this electric field is equal to the potential per unit length with respect to the ends of the conductor. So that we will substitute here. And again, if small n represents the electron density, free electron density, that is number of electrons per unit volume, n equal to n by V. Now we might confuse with the symbol, so let me call this battery EMF as epsilon, so that electric field is epsilon by L, and capital V as the volume, number of electrons per unit volume. V refers to the volume of the conductor. And suppose if the area of cross section of this conductor, if area of cross section is A, cross section, then number of electrons in this volume will be, number of electrons within this volume will be equal to n into volume of the conductor. So the current, the steady current, is actually charge per unit time. Now what is the total charge? It is actually the number of free electrons contained in this volume, and that is equal to small n, that is number of electrons per unit volume, into the volume, that is area into length of the conductor into the charge of an electron by the time. That is the total charge of all the free electrons within this volume of the conductor. So now we will substitute the associated values. So therefore, current, which is NALE by T. So this is NAEL by T. L by T is the length of the conductor by the time of flow of free electrons. So definitely it is equal to the drift velocity of the electrons. Distance by time, that is the drift velocity of the electrons. So this is Vd. So you can say that current is equal to, or you can write it in this form, current equal to number of electrons per unit volume, charge of an electron, area of cross section of the conductor into the drift velocity. So more is the drift velocity, more will be the current. That we can say definitely. Now as we all know that current density is current per unit area. So therefore this current density will be current per unit area, that is NEVD. If we go back to Ohm's law, which says that the potential difference applied across the ends of the conductor is directly proportional to the current flowing through it, provided physical factors like temperature, etc. remain constant. So this is what we know about Ohm's law. V equal to I into R being the resistance. So now here, instead of V, I will write epsilon because I considered the EMF of the battery as epsilon. So epsilon is equal to IR. Now epsilon is equal to, in place of I, if I write any LED, so we know that electric field is a negative of potential gradient. So if I divide this epsilon by L, I have to divide NEVD AR by L also. So this gives me electric field equal to NEVD AR by L. So from here on, we can find a suitable expression for conductivity, resistivity, and the resistance also. So we already had this expression, electric field is equal to NEVD AR by L, but we have also derived VD is equal to EE tau by m. VD was A tau and acceleration was charge into electric field by m. So now here we can write NE by L, instead of VD we will write EE tau by m into A into R. So this we already had derived. So now this E cancels out. What we have is ml, we cross multiply, ml equal to NE square A tau. E cancels out, NE square A tau R. So now R equal to ml by NE square A tau. So if we rearrange, we write ml by n square tau A. So this is the expression for the resistance in terms of the length of the conductor, the charge, the mass of the electron, the number of electrons per unit volume, and the area of the conductor. If you remember, we already saw in our previous classes that R equal to rho L by A, where rho is the resistivity. This rho is the resistivity. So if you compare both these equations, L by A remains same. So the resistivity becomes m by n square tau. So on comparing, we get the resistivity as m by n square tau. And you also know that the reciprocal of resistivity is conductivity. So conductivity, which is 1 upon resistivity. So therefore this conductivity becomes n square tau by m. Now we can express Ohm's law in a different form. We can express Ohm's law in terms of the current density and the electric field also. So this is resistance ml by n square A tau or tau A, whatever. The resistivity is m by n square tau and the conductivity is n square tau by m. The reciprocal of resistance is called as conductance. From here you will always get that n square A tau by ml will be the conductance. So now we try to express Ohm's law in a different form, that is in terms of the current density and the electric field. So again, with respect to the EMF of the battery, epsilon is equal to IR. So this is the EMF of the battery that we have connected to the ends of the conductor. So we know current is NEA PD. And we know about the resistance is ml by n square A tau. ml by n square A tau. Now, NEVD, if you see this expression, NEVD, this is actually the current density. A cancels out. Let me take L to this end. NEVD m by n square tau. Now, potential gradient, that is the potential difference divided by the length of the conductor, that is definitely the electric field. As we have already derived, NEVD is the current density, and if you remember, this quantity that we have already derived is the resistivity. So now I can write J equal to E upon rho, but 1 by rho is the conductivity, so this becomes J equal to sigma E. This is called as the vector form of Ohm's law, because electric field is also a vector, current density is also a vector. So this is called as the vector form of Ohm's law. Ohm's law, or you can say it is Ohm's law from a microscopic point of view, because V equal to IR, the current was itself a macroscopic quantity. Here we have introduced current density, and as such we can call this as the microscopic form of Ohm's law.